Hello, everyone. Can everyone hear me fine? Hope you had a pleasant lunch break, and I hope you didn't forget to grab a coffee afterwards. I don't want you falling asleep. We will present today about forensics, how to execute code on a forensics workstation. Just to run you through our agenda today. First, short introduction so you know who is on stage, who is joining us via Skype. We will talk about a vulnerability we found in a forensic Encase forensic imager. So popular forensic product by guidance software. We will briefly discuss on the fuzzing approach that we chose in order to identify the vulnerability, shed some details and some backgrounds on the vulnerability, and how we exploited the vulnerability. We also prepared a live demo, so if everything goes well, I can show you live and on stage how to exploit this vulnerability in Encase imager. And then we will close off with some, with an overview of the vendor communication and some general thoughts. My name, Florian Lukavsky. I work locally in Singapore as director for SecConsult, bringing SecConsult service to our APAC customers. With me via Skype is Wolfgang, who discovered the vulnerability, and in order to lower our CO2 footprint, we decided to bring him in via Skype and not to fly him over across the globe. So Wolfgang, say hello to the audience. Later on there will be sound too. Wolfgang, he's working as a security consultant, security researcher at SecConsult. So for the past 4 years, he has found many vulnerabilities in enterprise products, in security products. Lately, his security research is focusing on e-government systems and e-government communication protocols. So I'm looking forward to more vulnerabilities and more research from him. So very warm welcome, Wolfgang. Happy to have you here. But why do we actually do this kind of research? So little backstory, because before we get into the juicy parts. So we founded a SecConsult vulnerability lab where we bundle our research, where we do white hat security research. Since its foundation in 2003, we have published more than 200 vulnerabilities there, 200 advisories there. So if you're looking for some interesting stuff, check it out. Research fields that we focus on at the moment, on the one side, IoT, hardware hacking, strong focus also in the past years on security products. We feel that if you put in security products in your network, you want to add security and not actually increase the risk and increase the attack surface to your environment. Also one of the latest trends is e-government. And why are we doing it? We are also idealists, so we want to make the world a safer place. We also look at our own tools, at the own software that we are using to make sure that we are using secure products. So Encase forensic imager is one of the tools that we occasionally use. And of course, we also want to make our clients' environments more secure. So with that intro being given, I will hand over to my colleague Wolfgang.
Hello from Vienna. I am, as Florian already said, a security consultant here. Can you hear me?
We can hear you loud and fine. Just continue.
Okay, great. Okay. I will give a short introduction on the Encase forensic imager and the vulnerabilities we found. Yeah, so Encase forensic imager is a tool that allows allows forensic investigators to gather evidence from hard disks, flash drives, and so on, and also from physical memory. The idea behind Encase forensic imager is that it's a tool that can be used when the full commercial Encase forensic suite is not available. You can use Encase forensic imager to create an image that can later be analyzed by the full Encase forensic suite. Apparently, Encase forensic imager is a slimmed down version of the full Encase forensic suite. So a lot of code is shared between those two products, and also some vulnerabilities are shared between those two products. To our fuzzing approach, in order to find vulnerabilities in this tool that we use ourselves, we wrote a custom fuzzer in Python. And for this, we implemented several disk formats, several generators for disk formats, for example, FAT32, LVM, X3, MBR, GPT, and so on. And then we wrote a simple fuzzing tool that simply modifies some values in the header fields. For example, it replaces or prefixes and suffixes strings with long strings or format strings. It replaces integers with certain edge case integer values, yeah, and so on. As a result, we had a large set of mutated disk images of all different formats, disk formats, that we could use for fuzzing the Encase forensic imager tool. Here you can see an example of such a fuzzing implementation. In this case, this is for MBR partition tables. So here in the constructor, you can see that we set default values, same default values that are used in actual real MBR partition tables, and the generate method you can see here is used to generate a header based on the values that were specified here. Our fuzzer simply iterates over all the values that were specified here and replaces them with the aforementioned manipulated values. It then, for each iteration, it calls the generate method to generate one disk image for this specific format. Yeah, now that we had a set of a lot of manipulated disk images, we needed to find a way to try these disk images in Encase forensic imager and see whether Encase forensic imager crashes while trying to parse these images. For that, we used a simple UI automation script, and we used auto hotkey for this. So on the right, you can see a simple Python script that iterates over all the images and calls an auto hotkey script that then starts Encase forensic imager and loads the disk image and checks if Encase forensic imager crashes while trying to parse this. The problem, of course, with this approach is that it takes quite a long time to try all the disk images, so there might be still room for improvement with this approach. So after we have sorted through all the results from the fuzzer, and after removing all the duplicates, we were left with a couple of vulnerabilities. Probably the least interesting vulnerabilities are several denial of service vulnerabilities in the parsers for the X3, the ISOFS, the RISA-FS, the GPT file system parsers. An attacker could, or a suspect could potentially manipulate a disk image in a way that when a forensic investigator tries to parse one of these images, that Encase forensic imager simply fails. The next and more interesting vulnerability was a heap-based buffer overflow in the RISA-FS parser. This might be exploitable. However, we believe that it's not trivial to write reliable exploits that works on all systems. We also found a stack-based buffer overflow in the LVM parser, and this is definitely exploitable and can be exploited to gain code execution. I will, in the following slides, explain the vulnerability and how we were able to manage to write exploit that works for all systems. So a quick introduction to the LVM2 format. LVM2 is, if you're not familiar with it, is a simple abstraction layer that abstracts physical volumes into volume groups, and those volume groups can then spawn logical volumes. So the idea is that physical hard drives are abstracted into logical volumes, and the file system is then stored on the logical volumes instead of the physical hard disks. There is a file or a string called metadata that is stored in the metadata header of the physical volume. That this metadata string defines all the defines all the volume groups and the logical volumes in this physical volume. Here you can see an example of metadata file. So there's a volume group called test volume group, and in this test volume group there's one logical volume called test LV. So the vulnerability that we found was in the parser for exactly this metadata descriptor. Here you can see the pseudocode for the function that parses this metadata string. The part that is vulnerable is the part that gets the volume group name from this metadata string. So in order to get the volume group name, you can see on the right, the function first has to get the first line of the metadata file and then look for the curly bracket, and everything before the curly bracket is then considered the name of the volume group. So here you can see in the pseudocode, Encase forensic imager tries to find this curly bracket, so this one, and if it finds it, it copies everything before into this other buffer. As you can see here, the line that is read from the metadata file can contain up to 1024 characters. However, the buffer that stores the name of the volume group only can contain up to 256 characters. So if the volume group name is longer than 256, at this memcopy call, buffer overflow occurs. When this buffer overflow occurs, the stack looks similar to this. Here you can see on top of the stack, there is this metadata line. So the source buffer where the data is copied from. Then there is this buffer that are called overflow buffer that overflows. Then somewhere after that there is the stack cookie, the return address that is overwritten, and the stack frame of the caller. As you can see, if we wanted to overwrite the return address, we of course also overwrite the stack cookie. And if we simply let the parse LV function return, then the function would check if the stack cookie was overwritten. And if it is overwritten, it would simply abort execution immediately. So that's why we had to find another way to exploit this vulnerability. Luckily, the parse LV function calls, after the overflow occurs, calls a function pointer that is defined in an object on the stack in the frame of the caller. So we can simply override this pointer here in the frame of the caller. And after this overflow occurs, the parse LV function calls this pointer, and that's how we can control control the execution without having to rely on the return address. So in order to exploit this, these are our conditions that we have to deal with. There is no ASLR in place, which is good for us. There is no control flow guard. There is that data execution prevention is active. And the biggest restriction is that we can only use UTF-16 characters. These UTF-16 characters were translated from Windows encoding from this metadata file. So for example, if we specify AAAA in the metadata file, the buffer, the memory that we override would be overwritten with 4100, 4100, and so on. So that is one big restriction that we have to deal with. So the first step is to move the ESP into our return-oriented programming chain, into our ROP chain. To do this, we simply add this constant value to the ESP to move the ESP into this metadata line buffer. As you can see here, as a gadget, we have to always use valid UTF-16 addresses. So when we are at our first ROP chain, we have to deal with this UTF-16 restriction somehow, because in this first ROP chain, we are very restricted with the gadgets that we can call. There are only a couple of gadgets that are actually usable, so we have to find a way to deal with this in a way that we can execute arbitrary code. As it turns out, Encase Forensic Imager doesn't read this metadata file directly from disk, but instead it loads several sectors from the disk, this metadata header, into memory before copying this metadata into this UTF-16 encoded buffer. So when this overflow occurs, somewhere in memory there is this LVM metadata header that has not been modified by the application in any way. So if we could find this, we could store another ROP chain in there migrate execution to this ROP chain and then use all available gadgets so we can gain code execution. Luckily, when this overflow occurs, somewhere on the stack, there is a pointer that points directly into this metadata header at offset 40 in hex. So the idea is that we use this pointer on the stack to get to our ROP chain number 2, and this is where the actual ROP chain that executes code lies. So here you can see the gadgets that we used to do this. So the first gadget, we stored the EBP into EAX. Then in the second gadget, we pointed the ECX register to this address. And this address is loaded from the image, and it always contains the value of 18 in hex. We can then add this value to the EAX register, so that our EAX register now points directly to the pointer that we want. We then set ECX to the first gadget of the second ROP chain. I will explain in a minute why we need to do this. Then we dereference EAX, so that EAX now points to the offset 40 in this metadata header memory region. However, this gadget also destroys the first value in this region. So with the next gadget, we have to set it back to 0. As you can see here, the pointer that we have acquired points to the offset 40 in this LVM metadata header. However, our ROP chain begins at the offset 50. The reason for this is that we cannot store the ROP chain directly at this offset 40, because if we do this and the offset 40 is a value other than 0, then the LVM metadata parser of Encase Forensic Imager fails to pass this header. So what we do instead, we at runtime replace these 0 values with the first gadget that we set ECX before to. And this gadget simply pops the other 3 values from the stack so that we are exactly aligned with our ROP chain number 2. Okay, then we simply transfer execution to this second ROP chain. This second ROP chain removes the values from the stack, and we are at our second ROP chain with the ESP. The second ROP chain was simply generated with mona.py. It's very easy to automatically generate a ROP chain because the image is rather large, and therefore there are a lot of gadgets that can be used. So mona.py worked pretty great, and it generated the ROP chain that sets the protection of the memory region, and so that it can be executed, and then transfers execution to some payload. We set up our exploit so we can use any Metasploit payload with some size restrictions, And yeah, here you can see as an example the payload that simply spawns a calculator. I will now transfer back to Florian for explaining the scenarios that we can use.
Perfect. Thank you very much, Wolfgang, for the technical insights and explanations. Just let me jump back. I won't explain everything again. Jump back to the scenario. So basically what we discovered is a way to manipulate the LVM partition on any disk to allow for remote code execution once it's being loaded into Encase Forensic Imager and prepared for analysis there. So yeah, we have the scenario, flash storage media with incriminating data, check, brought all my incriminating data with me. To protect my incriminating data, I will add this manipulated LVM partition, so a specially crafted LVM partition to my flash storage. And then anyone who collects this or who finds this this flash drive and wants to analyze it, wants to collect evidence from it, can have it. And once it is analyzed using Encase Forensic Imager, the code execution will be triggered, and I will be able to run arbitrary code on the investigator's machine. And if I can run arbitrary code on the investigator's machine, I can definitely manipulate the evidence that he tries to pull off this device. Yeah, so let's look at it, how it will look in action. This is a live demo, so I hope everything will work out. Screen is back, so that's a good sign. I simply insert the thumb drive. So I already see a lot of incriminating data, a lot of sensitive information, which I keep on my thumb drive. I saved on encryption because I have the LVM protection. So then let's start Encase Forensic Imager. So you see we are running Encase Forensic Imager as admin user, so higher privileges. Makes more fun for code execution. So I disable now the write block check because I have directly attached the thumb drive, but it would work just as well via write blocked image gathering too. So I'm selecting the USB drive and preparing the image to be loaded. And I want to scan it for any LVM partitions. And here we have remote code execution. I mean, this is just a simple demonstration. So if we look back at the thumb drive, there are a couple of PowerShell and bat files down there. So some basic, a basic demonstration exploit. What the PowerShell does is basically run through all drive letters until it finally identifies as which drive this USB stick was loaded, and then executing any any files from this USB stick. This is one simple attack scenario. Yeah, but it's up to the attacker's imagination to tweak that, to make it more sophisticated, etc., etc. So for demonstration purposes, we pop up a simple screen. We could run a Locky variant now, a WannaCry variant now, encrypting the entire hard disk, demanding ransom from law enforcement to get back their evidence files. Or we can do whatever we want on that forensic machine. Any questions so far? Good, then, yeah, this was the live demo. Glad it actually worked. So who is affected? Yes, question.
Just a question. Is Encase forensic imager a very commonly used tool for forensic, or are there other alternatives?
There are other alternatives. Encase Forensic Suite is one of the more popular solutions that is out there. So that's by Guidance Software. So yeah, as we see in the following slides, there are definitely some big names that are clients of Guidance Software. So it is a fairly common and yeah, very accepted tool.
And another question is that is it usually the case that the image will be loaded directly from the drive, or will it be copied to somewhere else and then loaded from there?
Either way. So in typically, depending on the forensic environment that you have, you can either take a one-to-one copy of the physical evidence you have and work on the image, or you can directly via write blocker pull the image from disk. But in either way, since it doesn't matter if it's a thumb drive or a hard disk or yeah, some other form of media, as long as the disk image remains the same, and as long as the manipulated LVM partitions are being ported to that disk image, it will work when yeah, when a basically offline copy is used for further analysis.
But if an offline copy is done and you manipulate the offline copy, then the original will still be there for the forensic to maybe use an alternate tool to.
That is correct. So if you're not only relying on Guidance Software Forensic Suite, for example, on Encase Suite, but using other analysis tools as well, you can still circumvent that. Yes, that is correct. And also, if you deal with the evidence in a proper way, the original file, the original image will not be affected, because if you're pulling the offline copy via write blocker, as every decent forensic person would do, then the original evidence stays intact and unmodified, of course.
Okay, thank you.
Any other questions at that point? But I will be taking questions later too. So I'm not at the end of my talk now, but please, yes.
Has Guidance Software have they been informed of this issue, and are they doing anything about this?
Yes. May I answer these questions in 2 or 3 slides? Perfect. Good. Then back to the presentation. I'll be right back at your questions, so it won't be forgotten. Back to the presentation. Who is affected by this issue? Well, Wolfgang previously shared with us that Encase Forensic and Encase Forensic Imager share a large portion of the code base. We verified this vulnerability to be present in Encase Forensic Imager, which is kind of a light version of the Encase forensic suite. Some of the vulnerabilities he identified are present in both versions. This particular vulnerability, so this stack-based buffer overflow that we just found, appears not to be present in Encase Forensic. But then again, we are not the quality assurance department of guidance software, so we did not test all versions of Encase Forensic, but only a couple of versions that we could get our hands on. And yeah, some big names that guidance software lists as their clients is the US FBI, CIA, the US Department of Justice, Department of Homeland Security, London Metropolitan Police Service, Microsoft, Facebook, Oracle, so large organizations. What we know is that they are customers of guidance software, but of course we don't know if they're using this particular product, so Encase Forensic Imager, in a vulnerable version. But yeah, if anyone is using Encase, definitely worth checking. So what are the countermeasures that can be done? Of course, dealing with binary data, it always comes with a risk. It's always dangerous because you simply don't know what is coming at you. Challenging to deal with all kinds of different formats, etc., etc. So it is dangerous. Therefore, for forensic environment, there are basic hardening measures in place that should be used in order to limit the impact of any vulnerabilities that could be exploited. So usually forensic workstations are not attached to any network, so they are kept offline, not attached to the internal network, not attached to the internet. In many cases, a separate VM is used for each case to make sure that anything that could have gone wrong with the previous case won't affect future cases. But the purpose of creating those images, so this imaging process, which is the primary task of Encase Forensic Imager, is to create a trusted image that can be used for further analysis, can be used to gather further evidence. And well, as soon as it is possible to tamper with that imaging process, or as soon as it is possible to manipulate anything that happens after the image has been collected, the chain of custody is basically violated for this stream. And while the hardening measures are definitely good to have in place, the hardening measures will not prevent tampering of this specific evidence, because you're just imaging this evidence. So back to your question, if guidance software has been informed about this issue. So back in end of 2016, when we discovered the first batch of heap-based buffer overflow vulnerabilities, denial of service vulnerabilities, we as SecConsult follow a responsible disclosure policy. So we contacted the vendor, informed them about the information, gave them the information that we had collected, the proof of concepts that we had collected, in order for them to provide a patch. To our knowledge, guidance software did not provide a patch. So 50 days later, we released the advisory in accordance with our responsible disclosure policy. For the second case, the stack-based buffer overflow, which we demonstrated today, we identified that in early 2017, Wolfgang and René, two colleagues of SecConsult, they put quite some effort into it to create the proof of concept, to bypass all the limitations of UTF-16, etc., that were there to create a proof of concept exploit that would reliably work in order to assist guidance software in their investigations. But well, as you can see from the communications timeline, they pretty much went silent on us. And after escalating and informing them, we decided to contact various certs. So we contacted US CERT, CERT Bund, CERT AT, etc. about the upcoming release. And mid of May, we made the public release of this vulnerability. Since it's to this day a 0-day, we did not publish the exploit code. Back then, we published only a very redacted version of the advisory, so only giving some hints into where the vulnerability lies. But I guess the educated audience from today, I leave the exercise to you to come up with your own exploit. And the only response, so back to your question, that we received from guidance software, but also not directly, but via media, is basically that they believe that this is a very theoretical attack, that dealing with raw data always comes with a risk. They claim to have trained all their people on dealing with such kinds of risk. And in the last sentence, they basically tell us that they don't consider this issue to be serious and don't plan to do anything about it. And with this statement, I would like to conclude the talk and fade over to discussions, Q&A. So if there are any additional questions from the audience, happy to take them. Also, Wolfgang will be available via Skype for any questions that are too technical. Anyone? So I guess you're all working on creating your own exploit already. And thank you very much. Thank you for the attention.